Imagine a world where you own a box, not much bigger than a small microwave, and that this box can provide you with enough clean energy to power your home. Now, in that world, there is no need for an energy grid. It's totally redundant because the energy is literally as free to move as you are. The question is, what would you do in that world with such energy independence? Where would you go? How would you arrange your life differently? How could we, as society, arrange ourselves differently? Now, if you spend any length of time thinking about that, your imagination will quickly run wild with possibilities. Uninhabited regions become livable. Having a heated greenhouse in your back garden to grow vegetables all year round would be natural. Desalinating the ocean, irrigating the desert, growing crops in places where they haven't done for thousands of years, that would be a possibility. It's a super exciting future. That future, that box, the story of it is, for me, the story of cold fusion. It started about 30 years ago, and it is ongoing. Like any good story, it has its twists and turns, it has heroes, villains, greed, death, angels, all the good stuff that you would expect from a great story. People have even written whole books about the subject, both for it and against it, of course. The question is, where do I stand? Well, as my bio said, I'm interested in everything, convinced about nothing. This is one of the main reasons why I started doing experiments of my own. I want to see for myself, is cold fusion real? In essence, that box, could it be a possibility, or will it forever be a fantasy? Now, all this is to say that before we even get started, you shouldn't be convinced whether cold fusion is real or not just by listening to me talk. You need to do your own research, just like I am continuing to do mine. But what I hope you will be as we go through this is open-minded, because the realities of today, heavier than air flight, aka aeroplanes, continental drift, the efficacy of washing your hands between handling a corpse and delivering a baby, those are all considered to be utterly crackpot ideas in their day. And so with that open mindset, what I'd like to now do for the rest of the video is to give you a small slice of that story. And we're going to focus mainly on the human side of things for today and leave some of the technicalities for future videos. We're going to talk about what cold fusion is, of course, where it came from, why people get so animated about it, why were people skeptical about it. We'll talk about some of the skepticism. Then we'll talk about what an experiment, a typical cold fusion experiment, looks like, and we'll talk about what other people have done and some future thoughts as well. So a lot to cover, so let's get started. And we're going to start the beginning of our story, like any good story does, with the heroes. This is Martin Fleischmann and Stanley Pons, and they are seen here holding, in a sense, what could be described as a precursor to that energy box. In March 1989, they stunned the world by announcing that they had succeeded in doing something called fusion at room temperature on a tabletop chemistry experiment. This is something that in principle you could have done, and maybe you even did do at school. It's something called electrolysis, which we will come back and talk about more later on. Now actually there's a lot to unpack in what I've just said. So firstly, what is fusion? Secondly, why were people so excited about the announcement? And thirdly, why were people so skeptical? Why were they stunned by the announcement? Firstly, what is fusion? So typically, people encounter fusion in the beginning as the energy source of the stars. Stars like our sun that you see here. Just to give you a sense of scale, the Earth would comfortably fit inside this dark region, and you need about 12,000 images at this scale to represent the sun. So it is a beast. And in the center of that beast, it's 15 million degrees Celsius. And at those temperatures, the hydrogen that makes up the sun is running around incredibly fast, and the hydrogen smashes together at such speed that it fuses together, hence the name, and creates an entirely new element, helium. And in the process, gives off enormous amounts of energy that animates all life on Earth. So that's fusion. Now, why do people care about it? Well, it's because it's often described as the holy grail of energy. And the reason why is that, firstly, it is clean. So the byproduct of fusing hydrogen is helium, everybody's favourite party gas. No CO2, no radioactive waste. Secondly, the fuel is abundant. So the fuel is a special form of hydrogen that we call deuterium, and it exists, well, billions of years worth of it exist in all the water on Earth, both seawater, freshwater, drinking water, you name it. Thirdly, the fuel is incredibly compact. Its energy density is 1 million times more than the equivalent fossil fuels. And to put that into perspective, a typical glass of heavy water, so that's water that's only made of this special hydrogen called deuterium, that is your fuel for a lifetime, which is like mind-blowing. So that's fusion. Why were people so skeptical about Fleischmann and Pontz's announcement? Well, because fusion is the energy source of the stars. The only time we'd ever done fusion on Earth at that time was in gigantic machines like this one. This is JET. It is, as of today, 2020, the world's largest operating hot fusion machine, just south of Oxford in the UK. Now, in that machine, in the core, it is 150 million degrees Celsius, which is 10 times hotter than the centre of the sun. Just such a different proposition from what Fleischmann and Pons were claiming. So that's the first reason people were skeptical. The second is that when we do fusion on Earth, it always comes with radiation. Radiation that is so dangerous that anybody standing next to the machine would be, well, they'd be dead pretty quickly. And that's why these devices are encased in concrete shells that are several meters thick. But Fleischmann and Pons did this experiment in their lab, they were next to it, and they were fine. So you can see that there was reasonable skepticism. But what we should also remember is that yes, we should be skeptical about Fleischmann and Pons, but we should also be skeptical of the skeptics, which sounds a bit meta, but it's actually really important because the views of the early skeptics, they have echoed through the decades and still influence our views about cold fusion today. And so what I'm going to do now is give, in a sense, a critique of the skeptics in three ways. The first is on reproducibility, the second is on theory, and the third is on time. So, reproducibility, what is this? This is the idea that an experiment works the same way every time you do it. This is the ideal, the dream that every scientist is hoping for. But for cold fusion, it did not work like that. Some labs managed to successfully replicate what Fleischmann and Pons did. So reputable labs like Los Alamos and SRI International. But other very reputable labs, MIT, Harwell, and Caltech, they failed to replicate the results. So there was an inconsistency, and people made an enormous deal of this inconsistency. And for me, it is no surprise that there were problems in reproducibility. There are very often problems when you're at the cutting edge of science. Take, for example, Dolly the sheep. Remember Dolly? She was the first cloned mammal. She was born in 1996. Making Dolly took 277 attempts. A very irreproducible experiment that nevertheless rocked the world. So irreproducibility is not a problem for science, particularly in the early days, but it was a problem for cold fusion. So that's, in a sense, the first kind of black mark against the skeptics from my perspective. The second, theory. Theory is something that allows you to make quantitative predictions, accurate ones hopefully, about the outcome of future experiments before you actually do them. Imagine that I have a ball and I drop it on the floor. I can actually use Newton's theory of gravity to make a prediction about the precise time that the ball will land. And it's so accurate that I don't even need to drop the ball because it's such a good theory. That's the dream, again, of science. In cold fusion, the most continued critique is that no theory can account for the lack of radiation observed. That's the big one. For me, this is the biggest error in protocol that the critics make. And the reason is that it goes against the essence of science. Science, almost by definition, says observations reign supreme. And if your theory cannot account for the observations, assuming, of course, they're made correctly, we always assume that, then it is your theory that is wrong, plain and simple. And you have to go away and work hard to update it. And it might take you a long time, but that's how science works. Take, for example, superconductivity. This is the really cool phenomenon, well, literally cool, when you take certain materials, you cool them down very cold, almost absolute zero, and they lose all electrical resistance, which means electricity flows without hindrance. The theory of superconductivity wasn't developed until 46 years after the initial experiments. So theory is a kind of a nice to have, but if you don't have it, particularly in the beginning, it is not a problem for science. But it was a problem for cold fusion. So again, that's another kind of black mark against the skeptics. Thirdly, on time. Now, science does not demand speed. Now let's go back and think about Dolly. The confirmation that Dolly was indeed a clone took 18 months. It took a long time, not a problem. But for cold fusion, there was no time to waste, apparently. So the experiments which were the most high-profiled failed replication attempts, so those were at MIT and Caltech, they were actually done over several days. Now, the initial experiment by Fleischer and Pons took 10 weeks, so it's a completely different timescale. And in addition to that, within 5 weeks of the initial announcement, people were already at conferences claiming that Fleischer and Pons were delusional and incompetent, which to me just seems really odd when the initial experiments took twice as long. And after only a year, Nature, which is the kind of premier scientific journal, they had essentially declared cold fusion dead. For me, it just seems incredibly bizarre, the haste with which cold fusion was kind of discarded, considering the length of time that the experiments actually took. So that's the kind of the third kind of black mark against the skeptics. Now, I'm absolutely certain that there will be some people out there that disagree with what I've just said, and that's okay. It's worth remembering that people have written whole books about this, so of course I had to simplify things somewhat to fit everything into the video. I am well aware that Fleischer and Pons are no angels. They made mistakes of their own as well. The reason I highlight these 3 errors in protocol is because I think that they are severe. They are significant enough, in my opinion, to cast doubt over the overall consensus back in the 90s that cold fusion was crackpot science. That's my assessment, and you will need to make your own assessment, and that will require doing your own digging. One of the things I'm absolutely certain of is that the more you dig, the more you will realise that nothing is as clear-cut as you would imagine from doing a quick Google search. And the whole episode, for me, is just highly anomalous. So it's more important than ever to keep that kind of open mindset. And so as we keep that open mindset, let's dig a little bit deeper and ask, what does a typical cold fusion experiment actually entail? So back to this image, this is Fleischer and Pons again. We want to know what is going on inside this jar. They had some palladium, and that's a precious metal that just happens to love sucking up hydrogen like a sponge sucks up water. In fact, palladium can hold 900 times its own volume in hydrogen, which is kind of mind-blowing to think how much empty space there is inside of solid material. So they had a palladium rod and they put it inside of some heavy water. That's the water that's made of the special deuterium, which we spoke about at the beginning. What they did then is they passed electricity through the water and into the palladium. And what does this do? The deuterium that's in the heavy water gets slammed into the palladium and it is forced to suck up even more deuterium than it would otherwise like to. So you end up in a situation where for every 10 atoms of palladium, you might have 8 or even 9 atoms of hydrogen. So it's a really jam-packed environment in there. Under those conditions, what Fleischer and Pons observed is heat. Now, of course, there's heat because you're putting electricity in, things tend to heat up. But they saw excess heat. So heat energy that was so much bigger than could be accounted for through chemistry. It was of the order that you would expect from a fusion reaction. And the kind of smoking gun was really when other experiments actually detected the helium. And so you kind of had a connection between the energy and the fusion byproduct. So that's one way of doing cold fusion. It's called electrolysis. It's the primary way, I'd say, that people have been doing cold fusion over the last 30 years, but it is not the only way. I don't want to get into the weeds too much here and go into all the detail about what everyone is doing, but I think it is worth spending just 1 minute giving you a kind of sense of the landscape of the different types of experiments. So, firstly, palladium isn't the only hydrogen-loving metal. There are many others. There's nickel, there's niobium, there is zirconium, there's samarium, there's titanium. Second, the material that you have can be prepared in different ways. So Fleischmann and Pons had a rod, but you can make them in wires, you can make them in meshes, plates, foams, powders, thin films, you name it. Loads of different ways. And thirdly, there is more than one way to get the deuterium into the material, more than one way to load the material. Using electrolysis, or electricity, is the way Fleischmann and Pons did it, but you can simply put the metal into an atmosphere of hydrogen under high pressure. That's another way, that's what I do. You can also expose the metal to a deuterium plasma, that's another way as well. And all of these things have been pursued or are being pursued, and hopefully you get a sense of the diversity of different cold fusion approaches. The natural question at this point is, okay, 30 years has passed, there's apparently lots of different ways of doing cold fusion. What have we learned? What progress has been made? In particular, can we make experiments that are reproducible, that work every time, that produce meaningful amounts of power, and that can be controlled, that you can dial it up and dial it down at will? That's really what people care about, that sweet spot in the Venn diagram. Depending on who you talk to, depending on what you read, the answer to those questions is different. Some people say they have nailed it. Some people are more cautious. They create demonstration experiments for students to try out. Other people create companies based on their ideas and are incredibly vocal about their success, even though the details are very much lacking. And other groups are just completely secretive and you don't know what they know. So, just what is going on here? Why is it that 30 years on there is still such a lack of consensus? It is puzzling, and there is no single answer. I've been racking my brains about this for quite some time, and where I currently have landed is that I think there are two things at play here. First is about physics, and second is about people. And so let's start with the first one, the easier one in some sense, which is the physics. Now, if there's one statement that I'm confident to make about the science of cold fusion, it is this: that the make or break of cold fusion depends on the detailed nanoscale structure of solid materials. And what does that mean? It means that experiments are incredibly sensitive. Right? Just talk to computer chip manufacturers. They deal in the small scale when they're making their chips, and they spend billions of dollars on their factories to get it right. In the context of cold fusion, the details are things like, what material are you using? Is it palladium? Is it nickel? But even once you've chosen the palladium, it's different from manufacturer to manufacturer. The level of impurities are different, the way it's prepared is different, and even from one batch to the next, it can be different. And so it's very often the case that cold fusion researchers won't really know what it is that they're working with, not unless they have a lot of money and very precise equipment. And so for me, it's absolutely no surprise that we still have inconsistency in experimental results and therefore the interpretation of those results 30 years on. And now for the messy part, the human part. I think that research in fusion is different to other areas of research. And of course I would say this because I work in this area, but what it has that's different to other areas is that it has this saving the world characteristic about it. That's what pulls a lot of people in. This is providing limitless clean energy for the lifetime of the human race. This is the big one. Now, what comes with that territory is psychological things. You see, there is prestige associated with who can crack the problem, and also a huge amount of money available to someone who can successfully patent their ideas and defend those ideas in court, crucially. And both of those things strongly activate the ego, which is this irreducible part of the human condition, which is useful, it drives us, makes us want to succeed, but it also, left unchecked, can be very dysfunctional because it makes us over-competitive with other people. It makes us less intellectually honest, I think, about our own ideas and really whether they're actually any good. it makes us hold on to our best ideas for fear that somebody else might steal them, and we won't get the credit that we deserve, so-called inventor syndrome. Now, those things, I'm absolutely certain, have played a big role in the cold fusion story, and I don't have an answer to that one. There is no silver bullet for the ego, I'm afraid. So all I can say is what I think we should be doing as a community going forward. And it's based on a feeling, really, about how I think this century is going to be defined, which I think is about openness and transparency. The reason I think that is in the last couple of decades, we have really been transformed, I think, as a society by a piece of technology that has openness at its core. I'm talking about the World Wide Web, which I don't have to, tell you how important that is to our modern lives, right? It's what's making this happen and a whole bunch of other things. The reason it's possible is because of a choice that the inventor, Sir Tim Berners-Lee, made decades ago. His choice was to make it open, not close it off, not charge for it, not patent it like other people were trying to do. He famously said, "This is for everyone." An incredible gift that we benefit from every day, and of course we should be grateful for it. But I think what's more important is that we try and embody those open ideals in everything that we do, and not just in the digital world, but in the physical world as well. And that's where the real challenge is. But I am really confident that it can be done more in the physical world, because you have people like Arduino, this really inspirational company who manufactures small computers. Now, they made a really bold move to open source their computer designs so that other people could copy them and potentially improve on them. Now, of course, what happened was people made cheaper versions of them, but did Arduino collapse? No. It's thriving based on its open philosophy, and that makes me utterly convinced that if Arduino can do it, then cold fusion can do something like that as well. And so that's the driving force for me and how I do my research. It's what drives me to publish my research on GitLab in an open way. It's why I tweet about it. It's why I make videos like this. So hopefully I'll inspire other people who are interested to follow that same open philosophy. So if any of this open stuff is resonating with you, then obviously like and subscribe. That's a given. But more importantly, talk to your friends about cold fusion. Talk to your family about it. Go and find politicians and lobby them. Ask them, do you know about cold fusion? We need to be having more conversations about this topic because it potentially can change the world, and it desperately needs some more attention. And on that topic of attention, as always, thank you very much for being here. I really appreciate it. It's a long video this time, but I hope it's been useful as a kind of primer for what is cold fusion. Obviously, there's way more things that I could talk about. A lot of the technical things I haven't even touched on today. So things like what actually happens in fusion in a condensed matter environment. It's super interesting. What do I think about the recent work of Google, the Japanese work? There's so many more things to talk about another time. So in the meantime, if you have any ideas about topics you'd like me to deep dive on, please leave me a message in the comments section below. Thanks again, and I'll see you next time for some more casual physics.